to inverse problems that have a forward map, which is a pseudo-differential operator. And this is a joint work with Samuli, who is my main advisor at the University of Helsinki, Matti, who is also professor at the University of Helsinki, and Luca Ratti, who is a fellow postdoc there, and with the University of Modena and Reggio Emilia in Italy, which has been my former university for a few months, and is a joint work with Marco Prato, professor over there, and Mathilde Galinier, who is a PhD student, almost finishing her PhD. I think she's doing by the end of the year. Okay, so we saw yesterday what it is computer tomography, and that mathematically this can be modeled through the notion of the Radon transform. There is not much new with respect to yesterday on this, so mostly just the notation where we have that our target is denoted by U and the Radon transform is denoted by R. Omega here is the angle that gives us the information about the rotation with respect to the plane, and S is our offset. What happens in practice when you have a computed tomography device is that you have an X-ray source, then you have a detector, the source irradiates our object, which is with sort of weird shape here in gray, and the detector registers the incoming radiation as means of counting photons, and then the X-ray source is allowed to rotate all around the target when we are dealing with this kind of model of the Radon transform. There is a particularly remarkable property for the Radon transform is that if we consider its normal operator, so R star R, well, it can be proven that this is a pseudo-differential operator, in particular an elliptic pseudo-differential operator order -1, and even more importantly is a convolutional operator associated to the kernel that you see written down here, which is a Calderon-Zygmund kernel. Okay, so don't be scared by these details. This gives motivation to the work we did, but in the following I will just stick with the actually with the limited angle Radon transform. So we start from the Radon transform, but instead of rotating the angles all around the target, what happens is limited angle is that the sampling for the angle is limited in a certain wedge, which here we denote by minus gamma, capital gamma to capital gamma, which is a subset of minus pi over 2, and we denote it as R gamma of U, where U is our target. What's the difference when we are dealing with the limited angle tomography? Well, if we consider filter back projection, which is the main analytical tool to reconstruct when we have full tomography data, and this is something also yesterday was said in detail. Well, this is the kind of reconstruction you can achieve when gamma is 90 degrees, which means that we are sampling the whole thing. But if we keep using the filtered back projection to reconstruct our target, but we reduce the visible wedge of our target, what you notice is that there are some parts that are not visible anymore, and some tracking artifacts, this line here starts to appear in the reconstruction. If we reduce even more, these features that I just mentioned are even more evident. And the less the visible wedge is, the less the wedge that is visible is big, then the more this striking artifact becomes evident, and the less is the portion that we can actually hope to reconstruct from the data we measured. What is important for the work that follows is that some of the properties of the Radon transforms are to some extent applies also to the limited angle tomography. So R gamma is still a convolutional operator, but we have a slightly different kernel here. So the main part is the same, but this is multiplied by the indicator function of the visible wedge. Okay, and the normal operator, so R star gamma, R gamma, is not anymore a pseudo-differential operator, but this striking artifact that you see here are some discontinuities that follows this line, and this line actually at the same slope as the visible wedge, the area marking the visible wedge. And for this reason, the normal operator is a Fourier integral operator, which is a wider class of operator, which includes also discontinuities along lines. Okay, and all in all, what happens with limited angle tomography is that compared to standard tomography, this is a highly post inverse problem. So it's while regular or classical tomography, when you have you have a dense sampling for the angles and you have all the sampling for the detector cells, basically, where the problem is only mild ill-posed. Whenever you deal with limited angle tomography or some other limited data problems, the problem becomes even more ill-posed. So it requires more sophisticated techniques to deal with it. Okay, and just to give you some motivation of where does limited angle problems arise in actual applications, where there are actually plenty. One that is very close to the group in Helsinki is dental imaging, because the group in Helsinki, before I moved there, worked a lot over 10 years to develop this VT device. They basically developed a software to update the usual panoramic machine. This used, the technique they used was very close to what I'm gonna talk about in a few moments. So some sparse regularization technique with wavelets. Then another classical example of limited angle tomography is breast imaging. You can see an actual device produced by a company in Italy. It's actually placed in Bologna. It's called Giotto Tomo, and in their case, the visible wedge goes from -20 to +20 degrees, so it's only 40 degrees, and you only have a few direction from which the measurements are taken, which usually ranges from 11 to 13. So you see that it's not only limited in the angle, it's very sparse also in the measurement. And another classical example is luggage control at the airport. So even the machine that they use when you do the security checks to enter, to go to the gate, it's a limited angle computed tomography problem in practice. Okay, so what happens in practice when we're dealing with problems like a limited angle tomography? So this can be formulated as a linear inverse problems, meaning that our model reads as follows. We have the measurements here and in the following denoted by M, which is given by the limited angle radon transformer gamma times U dagger, where U dagger is the quantity we want to recover. So it's our true object, and there is some noise, perhaps epsilon here, which is unavoidable when we have measurements. These models photon noise, but also some modelment error that might occur when you do this. And here, just because we will need in the following, the amplitude of noise is controlled by delta here. And in the case of limited angle transform, we have that X is L2 of omega, where omega is a domain in R2, and Y is L2 of minus gamma gamma, so our visible wedge, and the space for the offset, so where the variable S lived, if you recall the definition we gave for R gamma. So this is a very standard approach, and to solve these ill-posed inverse problems, there are different approaches, analytic methods that I mentioned before. There are some iterative reconstruction techniques that are adapted from standard iterative techniques for radon from tomography in general. And then what interests us today is not only regularization technique, but a particular class among the regularization technique, which is sparse regularization. And these amounts of having the following model. So we have that we want to look for the minimizer over W, where W here are actually some wavelet coefficient of our target U. So this capital W here denotes the operator that associates to any U the sequence of its wavelet coefficient according to some wavelet basis. And the model has one term here, which is the data mismatch, which in the data mismatch, so some least square like term, plus the regularization term that does regularization directly on the wavelet coefficient. So of course, this is a very specific formulation. You can you can, in general, like define sparse regularization using different operators than wavelets. And also the other remarkable thing is that we are minimizing in this version directly on the wavelet coefficient. So this is what is called synthesis formulation, but there is a counterpart, which is the analysis one. But for the sake of today's talk, we need to deal with this kind of formulation here. And the other thing that we need is that in the following we will be dealing with an orthonormal basis of wavelet. Briefly on wavelet in 2D, in 2 dimensions. So here, like the images give the complete idea of what happens in the numerical counterpart. So imagine that this is your target, is a slice of a walnut. When you apply the wavelet transform, what you do is that you fix certain parameters. The first one you fix is the scale. So the number of scale you perform the wavelet transform. And in this case, for instance, you have 2 scales. And then the result is that you're gonna get from an initial image another image of the same size of the original target, and it is subdivided in square blocks, and each square blocks highlights property of your target. So for instance, here we have 2 levels, so 2 scales, and these coefficients here are in order the vertical coefficient, the so-called diagonal, and then the horizontal. And here, if we were to have only 1 scale, we would have the low pass coefficients. But if we iterate the composition again, we have another level of vertical, horizontal, and diagonal coefficient, and here is the low pass part. So what happens with the wavelet transform is that starting from your signal, you find a representation in another basis where your basis is entirely described by one function called mother wavelet. You also need the scaling function to define properly the low pass part. And then you generate the whole family starting by sampling the scaling coefficient J and the offset K, which moves around the plane. And the peculiarity of wavelets is that compared to more standard approaches like Fourier series, you can adjust the building blocks of your basis so that they can catch as fine details as you wish. Okay, you have this variable t here for us will denote the kind of coefficient we are dealing with. So either vertical, horizontal, diagonal, or f here is the low pass one. For what follows, we need a bit of notation. So in practice, what happens is that while when you define this kind of basis, this can, in theory, goes up to infinity. In practice, we only have a few scales when we perform this on a computer. And so if P is the size of our image, basically what we have is that we have J0 will denote the coarser scale and J1 the high scale. For all the wavelets that are not the finest details, we have only vertical, diagonal, and horizontal, while for the finer scale, we also have the low pass filter. And here K denotes the offset, so how we move around the plane. Okay. And if we now go back to the slide before here, where I laid out like this synthesis formulation for our problem, it is well known that a standard algorithm to solve this formulation is the Iterative Soft Thresholding Algorithm, introduced, I think, in 2004 by Dovesci, De Vries, de Mol. So it's a seminal paper in regularization theory using wavelets to carry out the regularization. So this gives an iterative algorithm where, given an initial approximation of the wavelet coefficient, then we update on the coefficient by applying this iteration. So to the previous iterate, we subtract 1 over L, where capital L here is the step size of the method. This guy here is basically the representation of the normal operator of the limited angle transforming the wavelet base applied to the previous iteration of the coefficient plus 1 over L, and this is we apply the operators to the measurements. And all this is then to all these we apply the component-wise soft thresholding operator. according to the parameter lambda over L. And what happens is that basically some of the coefficients, the smaller one, are put to 0, okay? And how many of these is decided by the soft thresholding parameter here. And the other coefficients are slightly, they maintain the same slope, but they are connected to the ending of the interval here. The interval of the coefficient that we put equal to 0, okay? So basically what the iterative soft thresholding algorithm does is that once we fix a maximum number of iterations, the map that goes from the measurements to W star of the approximation of the coefficient at the last iteration is an approximation of the solution map of the inverse problem, okay? So this gives an approximation of the U dagger that we would like to recover from our measurements M. Okay. So far is nothing really new. A step forward, which goes maybe a bit closer to the topic of this workshop, is that up to nowadays, it is well known that the ISTA can be understood, actually, the integration of ISTA can be considered as layers of a neural network, where basically if we take the main iteration, what happens is that we have this Kn, and then which basically contains the representation of the normal operator in the wavelet base, and the B vector here is the bias vector. And this can be defined like that independently of n, or we can make in the parameter theta all the weight coefficient coming from these operators k. We can fix the bias vector. We can possibly have other parameters that can be learned in the process, so the regularization parameter, the step size, n remains an upper parameter. And if we fix, call theta the parameter for our network, we can define the map f theta, which associate to M an approximation of our U dagger. And in particular, if we take theta to be theta 0, so we chose to fix k here to be this representation of the normal operator in the wavelet basis, then f theta 0 is equivalent to performing capital N iterations of ISTA. And if we look at the literature, this is just a few examples, the one that get our work started. We have the learned ISTA, or ISTA, from the paper of Gregor and Lecan in 2010, where they proposed, following this idea, residual neural network. There is a bit more recent paper where they proposed ISTANet, Zhang and Ganem. This is also a residual neural network. And another recent contribution is FBP ConvNet, where they propose a UNet, but the philosophy we apply in the paper is not enrolled. So this was kind of the main literature we looked at when we started working on this. And what we noticed was that at least these two contributions are not convolutional neural networks, and this one doesn't have as an endpoint to promote an enrolled scheme. So starting from that, we work towards having a representation or an explanation and understanding of the ISTA algorithm as a convolutional neural network. To do this, we did the following. So we considered the matrix, the operator K, which now is represent the normal operator of the limited angle transforming the wavelet basis. And we saw that this is composed by building blocks. And we denote each of these building blocks as this capital K with J going to J prime and T going to T prime. So what does it mean is that this block here identifies is the block that allows me to move from the element of scale J and type T to the wavelet subband of scale J prime to the T prime subband. Okay, and to describe this as a convolutional neural network, we need three rather standard operation in the theory of neural networks. So discrete convolutions. There is nothing mysterious. It's the standard definition of discrete convolution in 2 dimensions. Then we need downsampling. basically, in the theory part that I'll describe, this means that whenever we have something like these 4 elements in the matrix or in the block B, then we, after downsampling, we will have only this element B1 here. And upsampling is the reverse operation. So if we start from 1 pixel, this is enlarged to double the size and it's padded with 0. Okay. Once we define this operation, the following result can be proven. So I know this looks very nasty, but bear with me on the formula 1 second, and then I'll explain with an example what this nasty formula actually means. So we define this delta here, which is the difference between J prime and J, because this is going to be our multiplier for how many downsampling and upsampling we have to perform. And then whenever we are applying our building block K, J prime, T prime to the wavelet coefficient, which here are unrolled into one vector, what happens is that we distinguish 3 cases. If J is equal J prime, so we stay on the same scale, we simply convolve the kernel with the coefficient, but now reshaped in a 2-dimensional matrix. If J is larger than J prime, then what we do is that we first convolve and then we apply the downsampling, okay, so that we go to an element that has the same size dictated by J prime. If the situation is reversed, what we do is that we first upsample our wavelet coefficient and then we convolve with the kernel. Okay, and this is the final formula we can achieve. Why would we do that? Well, first, because we have a complete description of ISTA as a convolutional neural network, but also because compared to the representation that we would have of these operator in the wavelet basis, we reduce significantly the number of elements needed to describe it. So instead of having p to the square elements, this representation here requires only p elements. And now I'll try to explain this formula a bit better. So we start from an example. Imagine that our target is 64 by 64. So it is 2 to the 6 to 2 to the 6. And we consider 3 different scales. So we have one scale, which is 2 to the 5th, 1, 2, 3 elements, so vertical, horizontal, and diagonal. Then we have a second scale here, same elements, these are 2 to the 4th, and then the last level is also the low pass filter, and their size is 2 to the 3rd. Okay, so each one of these elements, for instance, this refers to the J equal to 4, and for instance, we pick the horizontal subband. The type of wavelet it's not important in this example actually. We have that this guy here is the component associated to this basis element of the wavelet transform. Okay, so we take J equal to 4, D is the offset, and for any type this doesn't change. So the first step is take the wavelet decomposition, and you get these building blocks. Then the next step is where the convolution actually happens. So pick one of these, but I warn you that this will be in our network architecture will be repeated for each one of these subbands. We now pick this one. So J equal to 4. When you divide 3 cases, you have J prime equal to 3, J prime equals to 4, and J prime equal to 5. So the easiest case, if you remember, is the case where J prime is equal to J. So what happens is that there is no downsampling, no upsampling. You take this kernel here, you convolve, and you get the result is the same size as the dimension of your starting building block. So in which case it is 31 by 31. 16 by 16, okay? And the convolutional filters you are convolving with is 31 by 31. Then when J prime is 3, what happens is that if you recall from this nasty formula, you first have to convolve and then you perform downsampling. So here, what happens is that you take this kernel, it's again 31 by 31, you convolve with this block, and then you perform downsampling so that the final dimension is 8 by 8, okay? And last case, J prime equal to 5, what happens is that you first have to upsample, and in this case, both downsampling and upsampling is just 1 is equal to 1 because J minus J of 1 is 1. Once you upsample, you perform the convolution with these filters that now are size 63 times 63, you convolve, and then you get this block. Why did you did we do this? And the endpoint is that at the end, if you see starting from these blocks here, we have exactly the right sizes to recompose our wavelet decomposition starting from each one of these blocks. So we have 3 for the level 5, 3 for the level 4, and 4 for the level 3, and we put it all together. And once we do this convolution for all these subbands, here there is a description of how to do this, and I wrote mainly for you to read it later if you take the slides. You get many of these coefficients, which we then sum it up together, and we get our version of the coefficient convolved with our filters. And this operation here is exactly what this formula is saying here. Okay, so this explains how to apply the normal operator of the limited angle transform when you do this operation in the wavelet basis. Good. So the last thing is that if you notice, while I was giving you details of how to perform these convolutions, what happens is that these filters are really, really large, and this is not the custom in machine learning, mostly because this implies a lot of storage needs and slow down the operation quite a lot. But what it can be proven is actually that we can carry out some sort of thresholding, but this is not, this word thresholding is a bit of an abuse of language. What it means is that instead of using the very large filters like that, we found a parameter tau that basically considers only the central part of the blocks, where the key is really with a box constraint given by the infinity norm. So we reduce the size, and this can be done without changing the result we gave to before, because this can be demonstrated to be just a perturbation of the ISTA algorithm. The convergence can still be proven by using the ISTA convergence properties, and finding a bound on these elements is not difficult, and in this sense from some properties of the wavelet basis. Okay. Then what I told you up to now actually applies to any operator that satisfies certain properties. So I told you the story about the limited angle tomography, but you can consider any operator A between two Hilbert spaces, and then these are the assumptions you need to prove the same result. Strong sparsity, the operator is injective, the operator is a convolutional kernel operator, so it means it satisfies these, where the kernel is a Calderon-Zygmunt kernel, which basically implies that then your operator is a pseudo-differential operator. And then you need the first order vanishing moment for your wavelet orthogonal basis. Okay, so this is pretty much all we needed to now finally define our convolutional neural network, which we call PSEUDONet. So starting from the definition we gave, the main iteration we gave for ISTA in the neural network format. Now imagine that this K here in particular is still our weights metric, so its coefficients are gonna go in our parameter for the learning, but this K is basically described as a combination of the upsampling, downsampling, and convolution that I explained to you in details with that example. And in this vector compositor theta here, we can put in also the regularization parameter, the step size, and then we have that the number of iteration and the tau that controls the size of our blocks is our hyperparameters. Then this structure for our networks, which our PSEUDONet, is that we can in principle do better than the standard ISTA algorithm, because for a choice of this theta, if you take exactly R star, W star, R gamma star, W, then you exactly have ISTA. But if you don't, and you do the learning of this weight coefficient, you potentially can reduce the numerical errors that you introduce every time you perform a discretization of the operator A star A. You mitigate the model errors in the definition of the operator A, okay? And what is even more important, you might provide in the end a representation in the wavelet base which is slightly different from the basis from which you started. And this might fulfill better the sparsity assumption on the solution. Okay. How this is done, what is the main idea beyond this approach is that our kernel K is understood to be split in two parts, K0 and K1, where K0 is the kernel of our normal operator and K1 is the kernel of another operator that can be learned. Okay, so this adds a bit of more information, and it's the part that can provide better result. So for the case of the limited angle transform, imagine that your kernel is something like this, and if you recall, these lines are intended because this marks the visible wedge in the limited angle tomography. This is split in two parts. K0, which is non-trainable, so this is something we pre-compute and we have. I'm going to show you example in a moment. And then this is the K1 part, which is size tau times size. So this is our hyperparameter for the size of the convolutional kernels. And this is the tribunal part, which we can prove that leads to another learned pseudo-differential operator. And this approach works also for Fourier integrals operator like the limited angle transform, because if you recall, in that case, we have that the most of information is concentrated in the center and possibly along these lines that that's the slope of the visible wedge. And this size here, so it means that what we're gonna do is that we are gonna optimize over the most important weights in our model, okay, where most of the information is concentrated. And this shape here, these filters here, we call them bow tie filters because they resemble a bit bow ties, especially if this box is small and then you really have a little tiny bow tie. Okay, we can prove convergence for the network. So we define the loss function is the empirical risk. We need to do some restrictions. So A needs to be restricted to subspaces XP and YQ. So basically we limit the wavelet basis describing the spaces to not be infinite. Then we restrict XP even more to the ball where the coefficient are bounded by this constant, and we need a probability density mu, so the result is not restricted to the peculiar mu we choose, but we need it to do the sampling. Well, we assume that eta epsilon is a random Gaussian random vector with probability density nu. So this is how it is distributed. And then theta star is just a minimizer of the loss function associated to the network f theta tau. So we can prove that the loss function is basically bounded by a constant C star that depends on the bound on the wavelet coefficient and the upper parameter tau, which gives the thresholding for the box inside the filters and the amount of noise that we let it go to 0. Okay, so now let's see how this actually works in practice. So we discretize everything here. There's nothing fancy. You just I introduced the bold face character for the discrete counterpart. This is our minimization problem, and we recover representation of the coefficient and approximation of the coefficient of the true solution. Now, I told you before how we perform the convolution, upsampling and downsampling, but I did not tell you how to build the filters. So these building blocks K with J to J prime, T to T prime. And here is how we build them. So we start from an image which belongs to the wavelet domain, and we imagine that all the pixels are 0 except to one activated pixel which is equal to 1. We apply the W star operator. This gives something that belongs to the image domain, where this pixel here becomes the pixel at the center of the image. Okay. Then we apply the normal operator of the limited angle transform. So you're going to have that you have this part here that gets elongated along the angular wedge gamma. And then when you apply this to the wavelet, you apply to this the wavelet transform, this is your filters. Okay, so our filters look something like this. What does it mean in practice? Consider a very easy image like this this circle. Okay, we first apply the wavelet transform, so we obtain something like this, where we have our horizontal, vertical, diagonal coefficient for 3 different scaling levels. We convolve with the filters, which means that we apply these filters derived up here, and we obtain a representation in the wavelet domain of this coefficient convolved with the filters. And then when we act with the adjoint of or the inverse of the wavelet transform, in our case is an orthogonal basis, this is the reconstruction we get of our target. And this operation here is exactly equivalent of applying R gamma star R gamma. Okay, so this is just how the convolution works, and the convolution gives exactly the same as applying the radon transform and this back projection operator. Now, after we have this behavior, well, the convolutional filters are applied to every wavelet sample. So this is the structure of the network, where the convolution that happens in the network that I exactly described to you before. So is very similar to the toy example that I described in details before. There are only 2 main differences. First is that for storage and efficiency of the network, we perform upsampling and downsampling always before convolving with the filters. And the other thing is that the downsampling is actually not defined as in the theoretical part, but is the more standard average pooling. Okay, the rest is all the same. So this is the structure basically of the network. And these slightly modification do not affect the main result, because they still amount as doing perturbation on the standard ISTA. Once we have done this, again, what it does is that our K here is converted into a partially trainable convolutional neural network, where only the center of the convolutional filters are learned. How much is the center is dictated by tau, and we put among the parameters that can be learned the regularization parameter and the step size L. Okay. And for our PseudoNet, we propose 2 different implementation, and I will explain to you why we have 2 different. So the very first one is the one that is closest to this idea of having the bow tie filters. So we imagine that our filter convolution operator K is split in 2 parts, which is our K0 and K1. What we do is that basically the central part of the bow tie filters, size tau times tau, are released for being learnable. So this becomes the part where we do training and we can learn the weights. And here in K0, these are left to be equal to 0. So they're fixed equal to 0. But we maintain, let's say, the coda or the tail of this of the singularities that comes with the limited angle transform. Okay, so this is fixed. Once I get my K, this is fixed. I put some 0 in the center. The center part is initialized as the initial kernel K, and then here is where we do the learning. Okay, so same structure as before, just this splitting in K0 plus K1. And if you think about it, how we are doing this is just a direct, this can be understood as a direct improvement of the backpropagation operator. And the structure of the network that learns here is exactly this one. Okay, so this leads to very satisfactory result, but it's very inefficient because the convolutional filters to produce accurate result have to be basically double the size of the original image, which makes it impossible to go over dimension 128 times 158, basically. So the second version of PseudoNet, or implementation of PseudoNet, so it's completely equivalent, but is way more efficient. So what we do is basically the kernel here, so this kernel here, this part, is actually implemented like this as a sequence of W, R star gamma, W star, and this is implemented with the radon transform and the wavelet operator. But plus, we have another term here, which is where the learning happens. Okay, so if you go back to this structure here, you have this guy here. Maybe it's a bit closer to this drawing we had going very quickly before that. It was here. Okay, yeah, so this was the structure. So this is our K0 and this is the trainable part, okay? So which we initialize at random, actually. Good, and then the role scheme reads like here, okay? So this is exactly computed with the operator, well, exactly to discretization precision. And then there is a part where you do the learning. And again, the learning structure here is the same as the architecture with the convolution, with the bow-tie filters, upsampling and downsampling I described. And also this has a very clear interpretation, because it can still be seen as an adjunct for improving the back projection operator. But compared to the filter-based operation described here, this is numerically more competitive and makes it possible to work with larger images. And this is the last note on this application, is that we saw that we have the standard ISTA iteration as the soft thresholding parameter, the soft thresholding operator associated to a parameter, and that parameter is always understood to be non-negative. Otherwise, we lose the definition of soft thresholding. When we were testing it, initially we left gamma to, we didn't force gamma to be positive or negative, and we noticed that sometimes it was picking up negative values, which led to us to, okay, we didn't really know what, this was not soft thresholding anymore. But when we enforced positivity on this parameter, for instance, by doing something like this, so gamma n becomes 10 to the gamma tilde n, where gamma tilde n is the actually trained parameters, result were not so good. I will show you in a bit. So in the end, we made some adjustment. So instead of having the standardly defined soft thresholding operator, we have something different, which for positive parameter is the soft thresholding operator. And whenever gamma n is negative, and this can be understood as some symmetric of the soft thresholding curve with respect to this line, epsilon y equal to x, okay? Good. So now this work, as I said at the beginning, is mainly theoretical at this point. So we have some preliminary result on the ellipse dataset, which are size 128 times 128, but we are currently working on two bigger images. The missing wedge is 60 degrees, and then here are the details about the training and the operator we used. Everything very standard. The results are with 120 layers, so iterations, and tau is 32. Okay, so this is the size of the center of the filters block, and these are some results. So filter back projection gives a reconstruction as you imagine, so many striking artifacts and quite blurry. And on the rightmost side, you see the difference between the ground truth and the reconstruction. With standard ISTA, we get better reconstruction, but still we see that the striking artifacts are rare. And then I will show you result for both the filter-based implementation and the operator-based implementation, where the soft thresholding parameter is actually a soft thresholding parameter, so it's forced to be positive. You can see, as I told you, that the reconstruction becomes very blurry. In both cases, they are comparable. Instead, when we leave this parameter to be to take also negative values, you can see that the reconstruction seems to do way better, and the result with the filter-based operation, the operator-based operators is quite similar actually, but these, remember that is actually can be extended to bigger images. I think I'm running out of time, so I have similar results here, but I'll leave you the slides so you can check them. I can maybe go to the conclusions. The results are similar, so you can draw same conclusion. It's just another example from our test set. Okay, so what I presented today is limited is a problem arising in limited angle tomography, but which falls into the broader class of inverse problem where the operator is a pseudo-differential operator or a Fourier integral operator. We saw that the standard ISTA algorithms can be understood not only as an unrolled neural network such as a residual network, but can be actually interpreted as a convolutional neural network. And the convergent result on the classical ISTA algorithm can imply the convergence of the convolutional neural network solution. Now, when we propose ΨDONet based on this result, and the main idea is that we split the convolutional kernel into two parts, one that is fixed and one that is the center part, which is left for learning. And how we build these convolutional kernels is that we can exactly prescribe from the theory the operation of convolution, upsampling, and downsampling. And while this might seem like we are forcing the network to do certain things, we notice that it leads to quite satisfactory results. And then we provided two different implementations, one that uses explicitly the filters to carry out these convolutions and this representation on the kernel, and one that does it in an operator way, so that it learns something more on top of the information we store in K0. And the idea behind this is that this theory we managed to develop kinds of combines and limits the part of deep learning and combines the knowledge that we have from traditional inverse problems. So this comes entirely from sparse regularization theory. So we have to some extent a clear idea of what is happening. And now, so as I said, we just submitted the work, which was mainly theoretical, but we are working on to extending it, especially on the numerical side. So now we actually finished training on the bigger images, 512, 512 on the ellipses, and we're training with both more realistic data coming from breast imaging. So that would be our end goal for that project. And we're working on the hyperparameter optimization and on the loss function. So we could consider additional regularization, but we're also considering different loss functions, for instance, with structural similarity metric, but in the wavelet domain, okay? On the theory side, we still are missing the convergence of the training network. So we're working on to the generalization problem. And the main message of this approach I proposed is that it works very nicely for limited angle tomography, but it could actually apply to any inverse problems which are convolutional kernels with and the pseudo-differential or Fourier integral operators. And some cases comes from seismic imaging for the geodesic X-ray transform, for instance, or the synthetic aperture radars. So these are classical examples where this technique could be extended. Okay, thank you, and sorry for going a bit over time. If you now have questions, I'm happy to answer.